Howdy, my name is Blake.
My name is Catherine Bernhardt.
I'm Kristen Waite.
My name is Jeffrey Fisher.
And I'm part of the TYTO Farm Surveying System. From a survey taken in 2019, there are around 2.02 million farms in the United States.
With an average of 444 acres of land per farm, that means there are almost 900 million acres of land growing the necessary foods for life, and this is in America alone.
Now 444 acres, even for a staff of 100 farmers, is overwhelming and serious problems can slip through the cracks. One of these serious problems is if specific plots of land are not growing at the expected rate. Poor growth could result from a multitude of things, including insect infestation, poor soil quality, underwatering, and much more.
In prior years, insurance companies have given out over $17.3 billion in payouts to farmers who haven't been able to provide sections of land with necessary nutrients. A lot of this is due to not adequately knowing what their crops need. Regardless of why these crops are not growing well, if the farmer doesn't know there is a problem, there is no way to address it.
Farmers are aware of this issue, so they have tried to come up with a solution. The current way for farmers to know if their crops are growing at a good pace is to walk through their 444 acres and measure random crops with a tape measure or a ruler.
Now this process could take weeks or months just for a small estimation, and certain areas could easily be missed. Also, the lost man hours in measuring crops manually can add up financially and take farmers away from something else more important.
After understanding the loss in time, money, and crops, we realized that there had to be a better solution to a measuring tape, and this is where the TYTO Farm Surveying System comes into play.
Named after the scientific name for barn owls, the system flies over crop fields and farms to spot any problems needed to be taken care of. The system includes a SICK TIM 781 2D LiDar affixed to the bottom of the drone. It also includes a Raspberry Pi for communication, Raspberry Pi camera for visuals, and a battery to power it all.
Also, the drone and its attached hardware are accompanied with the user interface in the form of an iOS app. To decrease total scanning time, instead of flying the drone linearly over each row of crops, we have decided to focus the drone flights on waypoints. These waypoints will be selected by the user, whether it be a farmer or a contractor company.
Once the drone arrives at each waypoint, it begins its scans. The unique aspect of the TYTO system is that instead of spinning the 2D LiDAR to collect 3D scans, our system spins the entire drone. This prevents adding over 1 kilogram of weight to the payload in a gimbal mechanism, and in turn, saving battery life and total possible flight time. These scans are then saved onto the Raspberry Pi, and once the system is connected to Wi-Fi, the data is sent from the Pi to the application.
The 2D LiDAR scans taken from the waypoint rotation have created this 3D model of the crop field, and once this data is received by the application, it is then converted to a heat map so the user can see all of the data in a clear and comprehensible way. At this point, the user can do what they need with the data and scan, using TYTO as many times as needed.
This solution solves many problems in crop growth monitoring. We estimate it could decrease weeks of work with 1 or 2 days of scanning. We also believe that our 360-degree spin will decrease that time by several more days, as the drone does not have to fly over every single crop and develop linearly scanned data.
This process is repeatable, cost-effective, time-efficient, and exciting. After developing the solution, we decided it was time to put our data to the test and see if it is a product that farmers would even need or want. After interviews with farmers around the area, we found that our idea is not only great for crop growth management, but so much more.
Using this exact system, we can determine grass density so that the farmer knows how many cows should graze on each part of the land, allow for accurate insurance estimation using plant density so farmers can get all of the money they deserve if there is a fire, drought, or more, and crop yield estimation so farmers can determine how much money they will be able to make after the harvesting season.
All of these other farm surveying needs that our system can solve makes it a multi-purpose, effective system that can be used all over the world.
This is a flow diagram of our whole system. There are 4 primary systems for TYTO: the iOS app, the Raspberry Pi, the sensors, and the drone. As stated earlier, on the iOS app, the user can set waypoints and view the LiDAR data. The iOS app then connects to the Raspberry Pi over Wi-Fi to send waypoints and receive LiDAR data. The Raspberry Pi handles all communication and computing on the drone. There is a SICK 2D LiDAR which talks to the Pi over Ethernet and a gyroscope that talks to the Pi over I2C. The Pi also tells the drone where to travel, and the drone keeps the Pi updated on its telemetry information over UART.
So this white plastic here is a 3D printed mount that we made, and as you can see, it holds the LiDAR so that it doesn't fall off the drone. It has the camera, it holds the Raspberry Pi and the PCB that we made, and then it has straps that connect the battery, and there are standoffs on the drone that connect this whole thing to the drone.
So here we have the battery connection. We have a Y junction that we've created to power with the battery. This is where the drone plugs in. Then off of that, we have the power input on the PCB. Then we have the power output on the PCB. If we're not connected to the battery, we can use this to power it.
So where we ended 403, we had this PCB, and as you can see, this capacitor is really large. And we also had to put double thickness so that this didn't hit the USB connections. As you can see, the updated PCB is a lot shorter in length than the old one. We have made the new PCB to have surface mount parts so the capacitor won't be in the way. This is the fully updated PCB. As you can see, we added this fan to cool down the Raspberry Pi, and all the surface mount parts make it a lower profile so that we don't have to have the double ports to integrate with the Raspberry Pi. As you can see, this is a much lower profile. So this PCB houses the buck converter and also gyroscope. And so here is where the LiPo battery connects to the buck converter. And we validated this all the way from 25 volts to 5 volts. It has a consistent 5 volt reading so that it powers the Raspberry Pi correctly.
We also have a UART connection. This UART is not currently connected as we're not connected to the drone, but this is where it would be. We also have a ribbon cable to power the Raspberry Pi camera. Finally, we have the Ethernet cable. This Ethernet is coming directly out of the Raspberry Pi, and this gray cable is then going into the LiDAR. The Ethernet connection is then used to receive the data from the LiDAR.
Once everything was on the drone, we then did a payload test to ensure that we were able to fly with all of the hardware on the drone.
So here I'm going to be showing off for the iOS app. Right here, we have the Raspberry Pi, currently running the REST server code in Python. Over here, I have the iPad app. It's connected to the same Wi-Fi network. And so the first test is to make sure that we can send coordinates from the app to the Pi. So when I press send markers, this will send these coordinates to there. So if I hit send markers, as you can see, all 4 coordinates were successfully sent. For this, we're going to be using the download scan function. So once we hit download scan, so check the status of it twice, and then it downloaded it here. So get LiDAR, that's the URL for getting the scan. As you can see on the app here, we have the scan, and it's dated with the time and date of the download. So once I load that scan data, as you can see, we've had our LiDAR data is scanned. It's showing up in the heat map, and it's showing up in the histogram right there. So as you can see from all these 2 tests, the iOS app is completely verified. It's able to send both the coordinates over the network to the Pi and receive scan LiDAR CSV files from the Pi to the app.
In this demonstration of the Autoflight Simulation, you can see the Raspberry Pi terminal that first demonstrates the user getting the data of the accelerometers. This is done to validate that we can receive that data to be used for the actual flight. Secondly, you can see the takeoff command being run. Moving on to the simulation view, you can see that the takeoff command causes the drone to fly into the air, land safely back onto the ground. After this successful demonstration of the basic simulation task, we decided to move on to more immediately important tasks for this project and move past the auto flight and auto landing for 404. However, it is definitely something we are able to make successful progress on, and recognize it as something we would take on if given more time.
The Raspberry Pi performs all the data collection. In flight, we use a software framework called ROS, which stands for Robot Operating System. ROS allows for us to interface with the LiDAR using 6 pre-made libraries. The LiDAR data is collected real-time and placed into a 2D point cloud. Simultaneously, we measure the gyroscope values to create a transform. We can apply that transform to the 2D point cloud, then add up all the point data in order to create a 3D point cloud. The finalized 3D point cloud is saved to a CSV file that is later sent to the iOS app. In 403, we had only been able to roughly demo this system. Previously, anytime we wanted to run the software, we had to open many terminal windows to execute each program individually. Obviously, this was not realistic for a drone that is meant to be usable by the average farmer. This semester, we were able to run all of our programs simply by turning on the Raspberry Pi. This way, the drone would require no user interaction other than through the iOS app.